the renewable chemistry and of a sustainable world to get the synthesis done. And some people call that also the technical or an artificial photosynthesis. And we named the project there called Rheticus, and I'm going to talk about in detail there. First of all, I divided my presentation into 3 different parts. Once I would like to motivate that renewables electrons can be a feedstock, a volatile feedstock for a sustainable material supply. Then I would like to introduce you into the project and show how this actually works, the artificial or technical photosynthesis. I comment on 3 core technologies: the CO2 to CO electrolysis in water, the PEM electrolysis, our Silysus 300, and anaerobic gas fermentation to use the feeds for bacteria. And then finally, I would also go into a deep dive and show some electrocatalysis work for the single step electrochemical reduction of CO2 towards hydrocarbons. And first of all, as I'm working in industry, we need to motivate electron as a feedstock. Can it become a business for a company like Siemens Energy? And the key is here to electrify the process industry. Usually it's not done by electrification. It's people are buying gas, oil, or coal and convert this to valuable chemicals. But to electrify the process chemistry, you have first to decouple the electricity and oil prices. It does not make any sense to make first electricity from oil or coal and then convert it back to a chemical. So we have to decouple this. And of course, there is a price or a cost limit necessary to do this. And nowadays we start to see electricity prices below 2 cents, and that price makes it actually attractive to work in this field. And then we have to do something very new in the field, which we call the so-called sector coupling. Usually the chemistry sector is buying from the energy sector electricity, or using components, as in the case of Siemens Energy, and produce materials there. But it has never been done before that an electricity company or an electricity technical component company provides chemicals to the chemistry sector. So that's really something new. And then finally, we will see electrochemical feedstock production versus a traditional petrochemistry. So we are looking to make our world new and sustainable. And this has been in the past also that the source of energy is linked to the energy sector in the chemistry field, because the chemistry sector always follows the energy market. At the beginning of the last century, we had mainly coal, so chemistry was using coal. Now we are in the area of shale gas, which followed to the area of fossil oil. And when this happened, that electrons will become a feedstock to produce materials, we will see radical new electrochemical production process in the industry. And also we see the electrochemical production of hydrogen, carbon monoxide, or ethylene based from our components like water or CO2. And then also the future may change in the chemical industry, that we see more decentralized locations, or that electrolyzers will be part of chemical plants. And why we are doing this? Because we are a so-called energy component producers, electron management company. We have generation, industry application, renewable, and transition in our business portfolio. And I personally are working in the new energy business field, creating such perspectives. What we would like to do is in the artificial photosynthesis to mimic nature. In the natural photosynthesis, sunlight is used and carbon dioxide and water to produce organic materials, we know in several steps. Artificial photosynthesis means that we utilize energy from renewable sources such as wind, solar, or geothermal, CO2 and water to produce valuable chemicals by electrolysis with a subsequent fermentation. That means we can recycle CO2 back as a waste from the atmosphere into the specialty chemical or into the fuels world. And we do so that we have two electrolyzers there. One is a so-called CO2 to CO electrolyzer, and one is a normal water electrolysis. We are producing syngas, and with fermentation, with an anaerobic syngas fermentation, we can then produce the specialty chemicals. So let's go now into the project. This project is a joint research initiative between the Evonik Industries and us. We are looking into materials like butanol or hexanol from renewable sources. We have started, and I show pictures for that, in September, our first pilot facility, and we envision about 20 tons production, 20,000 tons a year production as a potential target. The project actually started at the end of 2017. It's still continuing, and we are really starting to produce and to scale it up further. This is actually a view of our first lab setup. So this is a solar simulator, the solar cell, the electrolyzer here, the fermenters and bioreactors on the right. And in this setup, we could really produce butanol and hexanol purely from water, CO2, and sunlight. We were able to publish this paper in Electrocatalysts, and I would like to recommend this to read about this new value chain. There is also a video available either from Nature or on YouTube showing what we have been doing there. Would it pay off? It's very important in a chemical company that we show that it might pay off at the end. And here we have a schematic of our electrolyzers. It includes water and the CO2 to CO electrolyzer. Then this synthesis gas consisting of CO, CO2 and H2 is fed into a fermenter. And then we get out a certain amount of butanol from 1 kilowatt hour. So when we have 1 kilowatt hour of PV electricity, we will get out 45.6 grams of material of butanol in this case. And when we look into the efficiencies, of course, a PV cell has an efficiency of about 20%. The energy efficiency of these electrolyzers vary between around 50 to 70, but they are very selective. So we call this the Faradaic efficiency, or the selectivity is close to 100%. It's similar in the fermenter, where we are using two bacteria, Clostridium autoethanogenum and Clostridium cloiveri. They have an energy efficiency of 80%. Of course, they need something for life, but they are very carbon selective, and we call this here also Faradaic efficiency of 100%. So would it pay off? When we think about the cost of electricity, which I have shown before, that would account for 2.5 cents. And the price, not the cost, the price of 45.6 gram of alcohols is 4.5 cents. That means there can be a business case doing our new value chain. And in Germany, we had in 2017 about 1 terawatt hour, which could not be absorbed in the electricity net. That would amount to about 45,000 tons of butanol at a value of 55 million euro. So that means we can do something with it. So now coming to the first key component, the single-step electrochemical reduction of CO2 in aqueous media. So usually you think that when we put 2 electrodes in sparkling water, also hydrogen and oxygen could be formed. But the products formed at the electrodes is strongly dependent on the nature of the cathode. So when we have, for example, nickel, iron, or platinum cathodes, we only produce, as expected, only hydrogen. But when we have electrodes such as tin and lead, we are producing formate, the anion of the formic acid. The main product is CO when we would use silver or gold, so more than 90% are theoretically available. The only element which produces hydrocarbons is copper, and the range is quite wide, from methane, ethylene, ethanol, or some butanol even. But we would like to go early into a demonstrator, which means that we can only use CO2 to CO electrolysis which is now major enough to go into this demonstration project I'm going to show. How operates a CO2 to CO electrolyzer? We have a rather simple setup here. There is a gas chamber where the CO2 passes from the backside across the cathode. Then we have two electrolyte channels separated by a diaphragm, a standard iridium oxide, mixed oxide anode, and then we can use in this flow by mode the CO2 to CO. To ensure the stability of the electrode, we mix all the electrolytes together. The key component is here this gas diffusion electrode, which enables high current densities. And as I said, we are operating this electrode in the so-called flow-by mode. The electrolyte is composed of water and salts like, similar to baking powder, bicarbonate or sulfate. And we are using only cell components which are commercially available to scale up. So what are the results? Here you see in the first picture on the top, our very first electrolyzer in a fully automated test system, and we were also able to produce a tensile stack from it. On the bottom, you see that we have here a new possibility to describe this electrolyzer performance. We say because it's a gas-to-gas electrolyzer, we will have only a certain conversion rate, and this world record conversion rate in our case is around 35%. And this we could also get in the tensile stack. So we have already demonstrated 1,000 hours of operation, even on the tensile stack environment. And this is actually the world's largest CO2 electrolysis system, producing about 0.25 norm cubic meters of CO per hour. The next component we are using in a bigger system is our PEM electrolyzer. Here you see this 24 module array, and it has a power demand of 17.4 megawatts on 24 modules. The system efficiency is already very high, 75 and more %, because you don't see any pumps. We are using natural convection processes to be able to produce about 330 kilo of hydrogen per hour. And my new favorite topic is to study on this large scale in the megawatt range degradation issues on the 10,000 hour level. Coming back to the third component for this value chain is the syngas fermentation. There we have two types of bacteria. The first one is using the syngas to produce acetic acid or ethanol. Therefore, it's also called Clostridium autoethanogenum. And there is a second bacteria in the system which then condenses acetate and ethanol to butyrate, and the acetic, Clostridium autoethanogenum reduces then the butyrate and hexanol to butanol and hexanol, which is actually a direct substitute for gasoline today, and it's also a green solvent for different type of uses. Within our project, we were able, as you saw on the picture here and here a close-up, to scale it up to a 2,000 liter vessel with about 9 meters in height. To give you some expressions here, this is the facility in Marl, in the Chem Park, Chemistry Park in Marl. This is our container, and here in the back, in 9 meters height, is about the fermenter to produce butanol and hexanol. So what I showed you is that we could demonstrate first in the lab scale on a 2-liter scale, and now we are on the kilowatt scale of the electrolyzer and the 9 meter high fermenter, which produces about 15 tons a year. The scene was opened in Marl, Germany on September 21 by the head of our hydrogen innovation, Stefan Kaufmann, and our Ministry of Research and Education, Anja Karliczek. Coming back to now these key performance indicators, the natural photosynthesis has a photon efficiency of about 1%, is highly carbon selective, and uses a lot of water to convert 1 kilogram of CO2. We are already now at a stage where we are directly from sun-time 5 times more efficient than nature. We kept the high carbon selectivity, and we are using only about a quarter of the water which is necessary in the natural environment. And with that, I would like to get the last 5 minutes into a deep dive of electrocatalysis, because this is necessary to do that what I have just shown before. And as I also said, that copper is the only material which can convert CO2 in a single step, close to room temperature, to hydrocarbons back like ethylene or ethanol. And copper is really the key element most studied, and we have invented here a new, let's say, method of producing such electrocatalysis, which we call the template effect. We found out, I don't have, this can be read in the literature, that the initial state of this copper oxide is not influenced the product distribution. And therefore we have hypothesized that the starting material is also not the catalyst himself. It gets reduced under electrochemical condition and forms, let's say, aggregates of different surfaces, which we call the so-called oxide-derived structure. And we were able to show that this precursor here, paramelanconite, which is a natural copper oxide, has really high benefits. And you see here, going into the details, that it's an interdigitating mixture between copper oxide and copper 1 oxide and copper 2 oxide to form this tetragonal structure. And we published this, I show the citation below, one of the highest performances here ever in literature published. It has also the advantage that we can exchange elements in this system, that we can exchange, for example, the copper plus in the previous structure. Well, let's use this slide in this structure here, the red, by silver 1 elements, and keeping the space group. So we have here a medium to study different catalysts which originate from the same crystallographic environment. And of course, as we can exchange silver by copper or copper by silver, we can really change the D-band structure of the host materials. So this can be really changed in a very, very wide range. And we also can use other elements than copper to reduce the CO2 to CO or the or hydrocarbons. And we call this that we have the co-catalytic effect in the CO2 reduction reaction, and in the literature this is called the so-called spillover mechanism. And how important this is to have this is shown on the right. When we look into the distances which might be kept under the reduction in this new silver copper oxide precursor, we have, for example, a copper-copper distances of 2.9 or 3.4 angstroms, which are quite close to copper oxide. So if we see changes here, we might not have changes in the lattice itself. It might then originate from the substitution of copper 1 by silver, and this can be seen in the silver and the silver copper distance. For example, the silver oxide has distances in silver of 3.3 and 4.7 angstrom, and this dramatically changes in this new paramelancolite isomorph structure. The same is true for the copper-silver distances. And now to show what came out, it's very surprising and very interesting. So in the CO2 reduction reaction, so the substrate is CO2, we see a formation between a mixture between C1, which is carbon monoxide, and C2, ethylene and ethanol products. When we use CO, carbon monoxide, as a substrate, we can form a high amount of C2 products, which consist mainly of ethanol and ethylene. So here, this is the first time in literature that we have these dramatic changes just by the variation of one atom in a crystallographic structure, which isn't persistent. It's reduced under the electrochemical production conditions. And this is really a very high value of 92% of Faradaic efficiency at a current density of 600 milliamps per square centimeter. And we could really suppress hydrogen formation despite we are working in an aqueous media. However, coming back to industry, which is in my task to get a business case going, the template effect, which we have published now, is on the top 10 published with respect to selectivity and Faradaic efficiency. So actually, this paper holds 4 records in the top 10, which we published in Energy Environment Science just at the end of last year. The initial performance I showed you would be really sufficient to do industrial work. However, the stability of the catalyst still needs major improvement. The lifetime beyond 40,000 hours is required, and you see that we have, for example, silver segregation here when we analyze the catalyst on the back. And what I didn't show and didn't go into detail, the electrolyzer design needs electrolyte workup for continuous operation because ethanol will change the wettability of the electrolyte. And with that, I would like to conclude my talk, and I hope that I have shown that a combination of electrochemical feedstock production and anaerobic fermentation enables a selective and efficient way toward green chemicals and eventual fuels in a doable, efficient, and I hope in the near future profitable way. The single-step electrochemical reduction of CO2 to hydrocarbons still needs some major improvement in catalyst stability and electrolyzer design, but I think I have shown you that we are on a good way. And with that, I would like to thank a lot the Ministry for Education and Research, because they have sponsored this work by more than 10 million euros. And with those, I would like to conclude.